Recording. Sorry about that.
30%. 30% attendance.
Okay, let's start. So the class is called Signal and System. So actually we are trying to solve these problems in this class. Is like first describe what is the signal and what is the system, and see what is the interaction between them. Actually, for signal and system, you have input signal, system, and output signal. We see how they are going to be linked together. So remember these three questions. First, the question is describe a signal, and then describe a system, and describe their interaction, like the relationship among input signal, output signal, and the system. So for signal description, we have time domain description and frequency domain description. We have to accept this. We have time domain and frequency domain. They are both math, both not real. They are just numbers, but they are trying to reflect what is in physics. So time domain is just a function of time. This is pretty simple. And in frequency domain, we obviously this is a function of frequency. See F as hertz and omega as angular frequency. And sometimes we mention it as spectrum. So this is definitions. I'm going to try to, let's see what is going on here. I'm going to try to go over all the important concepts in this class. It's like, if you don't know what is something is something, you can go back to check this slides or this video. See if you can understand all the concepts in this slides. This can be used as a checklist for your final review. And so the important thing about this frequency domain and time domain signal is how you can convert between this. So what you get is Fourier operations. I try not to say Fourier transformation because they specifically refer to something you see in homework 4 and homework 5. There are 4 kinds of Fourier operations, and we saw 3 of them in the lecture. It's Fourier series we see in the beginning, and then Fourier transformation and DTFT at the end of the semester. So for DTFS, I didn't see them in homework. I didn't see them in the last year cheat sheet, so probably it's not going to be on your final. So you can forget about this part, but you see there are 2 aspects. It's continuous time or discrete time, and it's periodic signal or non-periodic signal. For periodic signal, you can do series, but for non-periodic signal, you can only do the transformation. But you can do Fourier transformation for periodic signal, but you are going to get spikes like the delta functions. Okay. So one very important thing to remember is this conclusion. Periodic in one domain is discrete in the other. So that means if you got a periodic in time domain, you get discrete in frequency domain. And you can use the other way. And the fourth statement is also true. It's like if it is not periodic, then it is not discrete in the other domain. It's like sometimes we say continuous, but I just want to keep the term periodic and discrete. And for continuous, I say non-discrete. And so let's just go to the next table. It's like this looks a little bit messy, but I wish you guys can understand what is going on here. So we have 4 transformations, right? And for each transformation, we have one direct operation, like go from time domain to frequency domain, and the other way back is like from frequency domain to time domain. So you see what's on the left-hand side of the equation is what you want, and on the right-hand side is what you already have. It's like, if I have the A case like in the frequency domain, I want to compute what is the time domain signal, I can use this equation. So for each operation, you have a pair of equations. Like And on the top is from time domain to go to frequency domain, and on the bottom is from frequency domain to go to time domain. But this part you don't need, but these three parts you need in the funnel. So as I said, there are two things, discrete and periodic. It's like this, take an example for a series. It is transforming periodic signal into periodic time domain signal into discrete spectrum. And because it's continuous and we see it is not discrete time domain signal, so you are going to get non-periodic non-periodic frequency domain spectrum. So, well, go back and look at this table and try to understand what is going on here. So another thing to know is like we want to go from continuous time to discrete time because we want to compute them in the computer. So we got something called sampling. And this is for this acquiring step is not very important. We're actually doing that in some experiments like ADCs and DCs you're going to see in other courses. What we care most is this non-crystal sampling theorem. Before I say Shannon sampling theorem, actually they're the theme. It's like the sampling frequency have to be greater than twice the maximum frequency. So for any problem that is going to be related to this sampling theorem is going to be using this equation. So mostly this one is given, but f max is not given. So what you are often doing is you use Fourier transformation to find f max. And aliasing, I don't know if it is covered because I don't see any problem in the homework, but aliasing is something like if it does not satisfy the conditions in the theorem, what will happen is like when you convert a continuous signal into discrete signal and convert it back to continuous signal, you get something else from the original signal. There is not a ideal converting back, so you get something more. And what is that something more? And you can get something from aliasing, but I'm not going into details because I didn't see problems related to that. Yes, and for Fourier transformation and for a series, as I said, you can do Fourier transformation on periodic signal, even though I say this is non-periodic to non-discrete, but this is a general thing. You can still do Fourier transformation on periodic signals, but what you get are delta functions, because, well, mathematically you are going to get exponentials and sinusoid and cosines in time domain, and their transformations are deltas. But the other way is not true. You cannot do Fourier series on non-periodic signals because the equation requires you have the length of the period. Okay, let's go to the description of a system. So before is everything about signal, and then we have the systems. So to describe a system, first is we have some properties of a system, as we see in the first few chapters, like LTI system. These are not complete description of the system. You cannot recover a system just by its property, but to describe a system, we can use other ways that can complete description of the system. Is we can use a signal to describe a system. The signal can be time domain and also frequency domain. And I'm going in the third part. In time domain, we use the impulse response HT to describe a system. And you should know what impulse signal is and what impulse response is. It's like you use the impulse signal as the input, and the output of the system is the impulse response. And in frequency domain, we have frequency response. You have only one problem in your homework that asks about frequency response, but it is pretty obvious because it is capital H, and this is lowercase h. there must be some relationship. Actually, this capital H is the Fourier transformation of this small h. But you still have other ways to acquire this frequency response. Like first way, you do the Fourier transformation of the impulse response to get the frequency response. Second way is like you do the Fourier transformation of the output, and you do the Fourier transformation of the input, and the ratio of them is the frequency response. Yeah. Two ways to do this. So, and the relationship between the input signal, output signal, and the system, if you just do it in time domain without any Fourier operations, you are going to use the convolution. The conclusion is that the output is the conclusion of the input signal and the system's impulse response. And in frequency domain, we have a convolution theorem. Actually, we are still doing the convolution in time domain, but we want to convert it into frequency domain and convert the result back to time domain. So the convolution theorem says the convolution in one domain is the product in the other domain. So what we are doing is like we have the frequency response, which is the Fourier transformation of the impulse response as one part, and Fourier transformation of input as another part, and find the product of these two parts, and you get the Fourier transformation of the output. Then you use the inverse Fourier transformation to transform the result back to get time domain result, time domain output signal. So, well, any questions?
I have a question.
Question?
If you have three things that are being multiplied in the time domain,
Yeah.
and you wanted to convert them into the frequency domain so you can use convolution
Yeah.
to operate on them, because for whatever reason,
Yeah.
can you actually convert just two of them, do the operation in the frequency domain, put it back into time, and then multiply it back with?
Yeah.
Okay.
Yeah.
You don't have to convert all the entire system.
You can, but you don't have to.
Okay.
Yeah. Well, I guess this is a little bit fast, but still try to use this slides as checklist. Like if you don't understand any concept in this slides, go back to make sure you know them, so that can help you in the final. So the next thing is about problem solving. It's like if you did the homework, like we come all the way from homework 4 is like we use definitions to solve Fourier transformations, and homework 5 we use tables like the Fourier pair table and the Fourier property tables. So why are we doing this? So if you see a problem and ask you to solve like a Fourier transformation of a signal, what are you going to do? So here the principle is try to avoid integrals as much as possible, and summation are the same. Try to avoid these things as much as possible. If you can look up the tables and get the answer, try to avoid using the definition of operations, inverse operations, also avoid convolutions. So as last quiz, it is much better that you use the Fourier transformation pair given in the quiz instead of using the definition. I just saw one guy can solve the integral by definition, but it is very easy to get the answer right using the table. So can I see this? So these are, well, I say pseudocodes help you to decide which method to use to solve your problem. First general question to solve is like calculate Fourier operations or inverse operations. It's like you have a signal and ask you to get its Fourier operation, or you get a spectrum to get its inverse operation. So first thing you need to know is decide which of the 4 operations you want to use. As we said, there are 4 kinds of operations. And for periodic signal, you can do Fourier series, Fourier transformation. It will be asked in the question, but sometimes you need to decide which pair of the equation you want to use. And it's like for each operation, you have the operation, the inverse operation, the pair table, and the property table. So there are 4 operations, so you have 8 equations and 8 tables. You want to decide which pair of equation and table to use in the beginning of a problem. And one special thing is about Fourier series. In Fourier series, if it in time domain just have sine, cosine, or exponential functions as each term, you are going to try to convert everything into exponentials and try to derive the answer by observing the terms. But if it is something else, then you will try this method. First, you would like to try if I can find any signal in the table that looks like the given signal. And so I'm going to look for the Fourier transformation pair table. If the signal I'm trying to find the Fourier transformation is similar to the signal I have in the table. So, well, I guess you guys are a little bit lost. This is what the final cheat sheet going to be look like. So as I said, you are going to have 3 pages like this, and on top it says discrete time Fourier transformation. Oh, sorry. I guess easier is this one. What you have already got is continuous time Fourier transformation. And you got the transformation, inverse transformation. This is nothing. This is, well, the properties. The property, in the beginning of property, we'll always say this is what is known. It's like, and you have the properties. So what is known, then these are knowns. These are the Fourier transformation pairs. Like if I have a delta, then its Fourier transformation will be 1. If I have 1, its Fourier transformation will be delta. And if the if the question asks you to solve what is the Fourier transformation of delta t plus 1 plus delta t minus 1. You want to use these 2 tables to solve this, right? So you see delta. So let's say, well, there's a delta here, right? It is something similar but different because I have plus 1 and minus 1. Then I'm going to go to the property table to say if there is any transformation, then I can have something, I can change this into this. The first thing I see is, well, I have linearity, so I can break this into terms and solve the first transformation of terms together and add them up together. Linearity property, then you use it. And the second is I have plus 1 and minus 1. Then let's say, oh, here it is time shift property. You have t minus something, and for this something here is minus 1. For this something here is 1. Then you use the property to solve the Fourier transformation instead of using integrals. And the definition will be related to integral. Okay, so this is a desired method that you always want to try at the first, if it is not a Fourier series problem. And second thing you can try is, well, it's not that you can try it. So everything else you have to use the definition equation. So the definition equations are here. You need to solve the integrals. So for 2 kind of problems, you have to use the definition equation mostly. So is if the signal is given by a figure, mostly you're going to use it use the definition equation. Mostly, if you are given a like square wave or triangle wave and try to solve the Fourier transformation of that, probably you need to use this. Or given by table. I'm not so sure if you have this kind of problem, but if you have a discrete time signal that is given by table, there is no way you can find a signal that is find that signal in the pair table.
What's the meaning of R2, page 12?
Yeah. This in the red parentheses are the problems that use this method. So R2 is review section 2, page 12, and H4 is homework for problem 5. And you can go back to check. Well, this is also used as a checklist to see if you can solve Fourier transformation by this method. Go back to check homework and review section slides. They are on Blackboard. And another problem is calculate the convolution. So it can happen like just ask you to compute the convolution, or it asks you the output signal of the system given the system description and given the input signal. It can happen both ways because the output signal is the convolution of impulse response of the system and the input signal. So there are many cases actually, but some of them are simple cases. For example, the first one, if it contains delta function, you can use the property of the delta function. It's like, should I write it down? So if you have a function x, time domain function xt, convolution delta t and shifted, then the answer will be t shift. The answer will be x shifted. So this is pretty easy, right? So when you see the one of signal is nothing but a delta function, then you can use this property very easy to solve the problem. Well, the second easy case is sorry, this is a third. Sorry, let me see. I'm sorry, there is no more easy cases. Sorry about that. So if they are given by like geometries, like the triangles, mostly triangles because you don't describe triangle in math, but it is easy when you do the integrals, you can just compute the area. If it is given by geometries, mostly you're going to use a definition. And if you are given signals like discrete signals, finite discrete signals like just a few numbers, 5 or 8 numbers, you can use a table like shown in class and some of the review session problem and the homework problem. But the most desired thing still, this is mostly if you want to solve an output of the system, mostly you are going to use this this method. This is you transform everything to the other domain, find the product, and transform it back by the inverse operation. And well, if everything fails, if you cannot identify the cases, just use the definition. So there is a very interesting case that you are asked to solve the Fourier operation of a product, like the Fourier transformation of a product. That happens a lot in your homework. And what I often ask is, what you are often doing is, you want to transform both to the other domain and do the convolution there. So mostly you can solve the problem by these steps. It's like for the previous slides, calculate the convolution is like I have two signals like xt. I want to copy the convolution of the other signal of ht, right? But so in the other domain, it is xf times h. But in this case, it is like I'm asked to solve in time. I'm asked to solve in time domain. It is the product ht, and in frequency domain, it will be the convolution. So what we are asked is the Fourier transformation of this equal to. By the way, one trick kind of writing your answer is never use equal sign to link time domain thing and Fourier frequency domain thing. If you have anything looks like xt something 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 equal to xf something something something, this will be wrong because this is time domain, this is frequency domain. They can never be equal. Never use this. So I saw a lot of these answers before, so I try to warn you, don't use this. But if you want to say the Fourier transformation of this is this, use the arrows, bidirectional arrows. This will make things more clear. And sometimes I will put f here, or what you can write is f curly braces xt equal to xf. This will make things much more clear. And another case is like you have a signal. You have one of the signal of the product is a step function. So your step function just defines a non-zero area, so you can use the definition for free. Because definition usually take the integral from minus infinite to infinite, and this step function will define the area more clear. Well, check out this problem. And if one of the signal is exponential j omega t, and well, you can use the frequency shift property as in your homework. But if it is this case, you can still use the method here. You can transform this into the frequency domain, the other signal into frequency domain, because this one in frequency domain will be a delta, and delta do convolution in frequency domain will just doing the frequency shift. Well, I should say if everything fails, you have to do the convolution definition again. Okay. Well, I try to use this as the checklist for your final review. This three solutions just cover the things after the midterm. So like LTI systems, and these things are not included. So, any question on this?
There's going to be sample files, right? Is there going to be a sample test?
Sample test? I am not so sure about that. But one thing is like, this is the first final review. Next week, Professor herself has a final review, and I'm going to have another review on Thursday. Time is not decided, and next time I'm going to do the problems. Try to cover everything that I'll try to cover everything after the midterm by doing some problems. I also have office hour on Thursday mornings. And
Do you know how many questions are on the test? Do you know how many questions are on the final?
Not so sure. Yeah.
Wait, when you talking about same time as usual next week?
Office hour?
Yeah.
Yeah. Basically, I have Thursday morning all morning. So that's it That